What if I say Newton's gravitational theory isn't really what we've heard growing up? Classical physics believes it differently, but quantum physics completely denies it in certain spaces. You must need clarification, right? So before delving into the contradictions of gravitational theory, let's have a flashback in detail. Every particle of the universe attracts other particles with a force. This is the theory Isaac Newton came up with in 1687, and since then, there have been no freaking laws to deny this phenomenon. Newton's law of gravitation was considered universal for all the objects in the universe, be it the sun, moon, stars, celestial bodies, or whatsoever. The attracting bodies are the product of masses with a square of the distance that is inversely proportional to the gravitational force. It was one of the most revolutionary ideas in the classical physics era that altered the understanding of the universe. But what most astros neglected is that Newton's gravitational law also has its own limitations. To be considered universal doesn't mean it applies to the big-ass space world. The universe is stretched beyond our fancies, and its big, massive proportion is still under the sheds. Hence, it's even absurd to conclude any law could be applicable similarly in all the planetary bodies. The Newtonian gravitation's limitations are endless. The law can't describe the bodies in a high-speed regime. At the speed of light, Newton failed to determine and predict the motion of objects. In cosmological scales, this theory again faced a backlash. The universal gravitation couldn't even structure the dynamics of the universe. It was out of its approach. Similarly, when you turn your head for the prediction of gravitational phenomenon, you'll be again disappointed. Needless to say, Newton also couldn't successfully predict the existence of black holes and gravitational waves, which are ripples in space-time. But despite such denials, the gravitational theory is still considered universal, this time with some limitations. However, thanks to Albert Einstein, he came forward as a physics savior in the 20th century. His theory, hypothesis, and whatever this guy brought into the limelight was a huge hit. So as that, Einstein's theory of general relativity took over the Newtonian gravitational law. It can predict the motion of objects at the speed of light, determine the existence of gravitational waves, explain the quantum realm, and structure the dynamics of the universe much better than Newton's law. However, at certain points, general relativity also has limitations. Einstein couldn't successfully describe the black hole centers and singularities phenomena, and even failed to predict the existence of dark matter and energy. Also, when it comes to describing the behavior of the universe on observable scales, it can't determine a complete description of the universe as a whole or its ultimate origin. To be specific, general relativity is the leading theory in physics, but the limitations are also worth mentioning. Not in one freaking way, the incomplete explanation of certain phenomena implies the failure of Einstein's relativity, but it opens another chapter of explorations, fascinating, and research. However, as you have seen, when Newton's gravitational theory failed at explaining some phenomenon, Einstein took over. But here's the catch. A new study from scientists in South Korea's Sejong University showed that both Einstein's and Newton's laws aren't valid for binary stars with long periods of separation. These binary stars are also known as wide binaries. This is a system where two stars are gravitationally attracted to each other and orbit a common center of mass, but their distance isn't as regular stars in the solar system. Their distance is measured in thousands to 10,000s of astronomical units, or AU, where 1 AU is the average distance between the Earth and the Sun, but still, they are attracted mainly. However, wide binary stars are relatively easier to observe because the individual stars can be more readily resolved and studied. That being said, the formation of the binary system can result from various stellar mechanisms, including the fragmentation of molecular cloud into multiple protostars, or the capture of a passing star by an existing star to form a binary system. God knows what the actual forming mechanism would be. It's also worth mentioning that the longer the gravitational perturbations between the two stars, the more likely these stars can affect their orbits and cause orbital changes, which could widen or narrow the separation between them. The researcher Kyu-Hyun Chae used the European Space Agency's Gaia Space Observatory to research 26,500 wide binary star systems in the 650 light-year range. While studying this binary system, a strange phenomenon piqued his interest. He noticed that when these binary celestials have an absolutely minimal orbital acceleration, like somewhere around 0.1 nanometers per second squared, the observed acceleration gets higher, about 30 to 40%, which is quite unusual to observe in contrast to the Newton-Einstein theory. But when the low orbital acceleration was greater than 10 nanometers per second squared, they behaved exactly according to the Newton-Einstein theory of gravity. This was totally unexpected and strange. On the contrary, if you see this phenomenon as a limitation, your mind will blow up again, as it suggests something unusual is occurring specifically at these extremely low accelerations. However, in the standard understanding of gravity, this mysterious concept is related to dark matter theory, even though what dark matter really isn't completely understandable yet. Some hypotheses say this is something most of the universe is made up of, but we don't know much about it. When some celestial objects don't behave as we'd expect based on our normal understanding of gravity, Astro says the dark matter might have something to do with this strange behavior, but no one is dead sure. Despite the dark matter theory, modified Newtonian dynamics is also widely considered the reason behind this peculiar phenomenon of binary stars. It was first suggested by an Israeli scientist named Mordechai Milgrom in 1983, who was sure that MOND might be able to describe the galaxy's unusual phenomena instead of dark matter. Not only does this modified theory help explain those odd behaviors, but also the unusual things we see in galaxies. However, we've got another exciting theory for you. After dark matter and MOND, another theory came up, which was inspired by the modified Newtonian dynamics, co-authored by Milgrom. The theory is known as AQUAL, an abbreviation of a quadratic Lagrangian. As per the scientists, AQUAL can elaborate on gravitational anomalies or modifications to gravity. This can also explain the unexpected boost in acceleration that could be 1.5 times higher than expected. Though this AQUAL theory is somewhat speculative, scientists firmly believe that AQUAL is a better explanation of weak gravitational forces than our standard grasp on gravity. Nevertheless, none of the above discussed theories is universally accepted within the scientific community. Most astroscientists argue that observed anomalies in wide binaries may have alternative explanations beyond modifications to gravity. They challenge the studies of AQUAL and MOND to explain a broad spectrum of phenomena, from galactic dynamics to the behavior of light in gravitational fields. Some scientists don't give a damn about MOND, AQUAL, or dark matter. They are dead sure about the standard gravity model as described by general relativity. To them, this theory is exceptionally successful in explaining a number of gravitational effects and has withstood numerous experimental tests. They even believe that general relativity can only describe the wide binary system with further investigation. Additionally, the anomalies in the wide binary system have several significant implications for the field of astrophysics. This concept challenges our understanding of the universe, which has been described by Newtonian's law and later by Einstein's general relativity for centuries. But at the same time, the wide binary system became a valuable laboratory for testing gravitational theories under unique conditions. It allows scientists to explore the deviation in standard gravity and if it occurred in specific contexts. However, it's also worth mentioning that MOND and AQUAL might not be accepted universally, but they broaden our knowledge about the universe. From one aspect, modified Newtonian dynamics provides alternatives to the concept of dark matter. As dark matter suggests a range of gravitational anomalies in the universe, AQUAL means that these anomalies could be due to modified gravity instead. This opens up an area of investigation and curiosity in this area of science. Furthermore, this may give insight into galaxy dynamics, including the distribution of visible and invisible matter and how galaxies evolve over cosmic time. The research on wide binaries is still on the go. Scientists strive to find new concepts and theories each day, so concluding the final analysis would be absurd. Let's end the video here. Make sure to comment below with your take on the wide binary system.